He's working at present there as a director. He has a very vast industrial experience of 17 years in execution of multidisciplinary tasks that include hands-on with project qualification and budget allocation in United States dollar for offshore clients, designing the CFD computer-aided engineering simulation architecture of spectroscopic products through laboratory experimentation practice, ensuring thermal stabilization inside the optical system of different spectrometers. Prior to joining Beacon India Private Limited, he worked in several other organizations, companies. Some of them are like Sirtech Solutions Private Limited. He was working as a principal architect since 2020. Then prior to that, he was working with, which associated with Amtech India, where he worked for quite long years, from 2011 to 2020. He was working as a thermal architect in Amtech India Private Limited. Then prior to that, he also worked in Mentor Graphics as a mechanical analysis, as an application engineer in the mechanical analysis division for more than 4 years, from 2007 to 11. And his background education is his PhD in CFD and thermal science from Jadavpur University in the year 2007. And then prior to that, he was did his undergraduate degree in BTech in mechanical engineering from College of Engineering and Technology Bhubaneswar under Biju Patnaik University of Technology in 2000. So this is all about the very brief introduction of Professor Dr. Sarkar, and of course I may miss some of his industrial experience. If I miss, please pardon me. And now I would like to request Dr. Sarkar to present his lectures. Dr. Sarkar, please.
Yeah, thank you, Dr. Rath, and good morning to all. Thank you again for a nice introduction. And your introduction actually little made me nostalgic in terms of the spectrometers. Yes, I spent a very long time in the spectrometer and spectroscopic devices. So from there, this actually, I done my PhD in the field of radiation and convection, as you know, but then eventually in the spectroscopic segment, I got introduced to the phase change because I'll just give a brief, which are not there in slide. In a typical spectroscopic equipment, if you see, there are various type of spectroscopic devices. Out of that, the one primarily which does the chemical synthesis of samples, so it runs by a technology called ICP, which is inductively coupled plasma. And during the plasma, so there used to be a torch. Inside the torch, outside the torch, there is a very high voltage electromagnetic coil, and that electromagnetic coil will be excited in a range of somewhere 27 to 40 megahertz. And in that excitation range, the inside, because this coil will be surrounded on the glass torch. It's a quartz torch, and inside the quartz torch, this sample will be, the chemical sample which need to be synthesized, they will be atomized, and in the atomized form, they will be injected inside this torch. And now, because of the electromagnetic high voltage induction, so this atomized particle will be getting heated up in the range of somewhere 9,000 to 11,000 degree Kelvin. And obviously it will illuminate with different light spectrums. And the moment these particles will illuminate with the light spectrum, our spectrometer, we have the arrangement of the spectrometer with prism and other optical devices, which takes the exact ray with the respective wavelength to detect that what are the composition behind the sample. But in this whole process, I'm not going to the spectrometric optical system details, but then my interesting area was when this atomized particle, or it will get introduced in this torch through the nebulization process, all the particle doesn't get used to ignite. So a few particle will get ignite and remaining particle will it will get deposited over the glass surface. And since the temperature of the, you can imagine inside, because of the electromagnetic induction phenomena, the temperature was going up to a plasma level, and because of this temperature, the glass also will be heated up significantly. The quartz surface will get heated up, though we used to have some diamond coating and some graphite, very polished coating. But then since it is too much heated up, any accumulation of the droplet used to crack the glass at the customer's interface, at the customer's places. So we faced a lot of challenges, because one glass torch used to cost us around approximately $2,000. So that's a huge cost, which customers always, reluctant to spend, always, because of just a crack. So we had to address this part, and that was the introduction, that we really wanted to understand how the droplet behaves there. That was my introduction to understand the field of droplet dynamics more closely. We used some of the commercial tools, but then the results were not satisfactory, because in commercial tools they supported mostly up to equilibrium plasma, but the non-equilibrium plasma part they did not support. So hence, I developed my own code on that, and I got a significant amount of exposure in that. So that's the exposure. So hence, Dr. Rath, you reminded me that particular period of my laboratory experiments and numerical computation. So with that experience only today, I am, I'm very much happy that I got an invitation from IIT to present my research work carried out then. Thank you very much, and let me start this. So today I will obviously, I will be speaking on mostly on the phase change processes and its potential application. And now I am responsible for promoting the simulation range of products of SolidWorks. And obviously in our SolidWorks simulation, now Simulia and Abacus and Xflow, all the important high-end simulation solvers get introduced inside SolidWorks. So SolidWorks have a huge simulation community. So obviously I'm responsible to put forward that. So a mixture I'm going to present to how the phase change process is and its application, and how SolidWorks represents it in the later section. So this will be today's overall agenda of my presentation, and let me start with the so if you can see, I mean, just a brief understanding about what exactly a phase change process. So if I let me change it to my pen mode. So this is a typical, all the concept what about phase change we generally occur in the class 12 syllabus, a very base level, that is, anything gets converted from solid to liquid, and the state gets changed because of the heat addition, and then from liquid to gas, and then gas to plasma. Okay. And then in the case of sublimation, yes, there are some direct transfers from solid to gas. Now, if I little bit elaborate it on a typical process of solid, liquid and gas, then this diagram will be very much realistic diagram, which will give an understanding how the solid, liquid and gas exactly interact with each other in this pressure versus temperature plot. And you can see the triple point, and then the melting to freezing point, the vaporization to condensation point, everything in a very much compact and very much technical way. This diagram will represent the transformation happens from solid to liquid, liquid to gas, and eventually solid to gas. This is a very famous diagram. I feel it's a self-explanatory. Just I'll tell it. People already understood by seeing it. This is a typical, phase change diagram. I have put it for water. So you can see the moment, we heat up the water, the main thing, it first in the solid state, it first, the temperature will rise as you are inputting the heat. and then it will reach up to the freezing point, and then there it will start melting. So this is the part is the BC part, which is takes care of the melting part, and we say that is the latent heat of fusion, which takes care of the energy absorption part. And exactly when we reach this state, when the transformation happens from solid to liquid, we say it as phase change, and it remains as an isothermal process, because as you are adding the heat, it is being absorbed in the latent heat of fusion. So the temperature remains there, and approximately I collected a data. It's approximately, it has been seen that it is around 2260 joule per gram. This amount is, and then once the whole ice transform to liquid, and then obviously the whole liquid temperature will go up again, further adding the heat. And then again at the vaporization, the same thing happened. The phase change happens again, the vaporization, and we claim it as the latent heat of vaporization. And this is approximately 334 joule per gram. And from E to F further, the gas will reach, it will go further heated and superheated region. Now the main player of this phase change phenomena, that is interface. If a driver, the main driver of this phenomena is interface. So the study of phase change is nothing but the study of interface. So the interface is a very wide definition. Let me start with, like, interface between the phases has very different properties. Now the basic concept is how we define the interface. In the coming slides, you will get to know that the main concept behind the interface is the change in the property, certain change in the property of the fluid between, certain change in the properties exactly during the interface, because the interface held between two different fluids. Now that's a very important and crucial understanding we have to set up, that how to define that particular interface at every numerical step, so that the property at the interface will be correctly captured at every numerical iteration. And you can see here that interface may control between phases, liquid to liquid, liquid to gas, and gas to gas phases. And because of the small extent of the interface relative to the bulk, small changes in composition of the interface may have large effect in the interfacial properties. Of course, that is obviously we are going to further look at this in the coming slide in a more detailed and descriptive way. And this can be exploited for all kinds of chemical and vaporization process. Now, if you little come down, boils down from interface definition to the little bit micro level further, that is the main role is taken in this interface dynamics is surface tension. Now, let's see what are the forces which are there inside a fluid, especially when it undergoes a phase change. So there are mainly two different types of tension. One is interfacial tension and one is surface tension. Now here we have to understand fundamentally the interfacial tension and surface tension. There is a principally, it is different. The surface tension which act exactly parallel to the surface, okay, exactly which is holding at the interface, you can see this is completely parallel to the surface. But the interfacial tension very near to the interface, if you see the intermolecular forces, that forces prevails across the sphere. Okay, so in every direction these forces exist, in this direction, in this direction. So this part is the interfacial tension, and the difference between the surface tension and interfacial tension, this has to be understood. Now, however, the main forces involved in interfacial tensions are the adhesive forces between liquid phase of one substance, either a solid, liquid, or gas phase of other substance. That is obviously. So this part has to be understood with little more importance. The interaction occurs at the surfaces of the substance involved, that is at their interfaces. This is a very much we played in our childhood days, when we started understanding the natural phenomenon, how the natural phenomena happen. In our childhood days, we used to see that yes, the if we put some oil on the liquid or any water or something, I used to remember, that's a very crazy part. I used to um, admire that how the oil getting is floating over the water. And yes, I used to try to mingle it. Why it cannot mingle if sugar is getting it's mingling? So we used to try, and then exactly the thing used to happen is the oil will form a small droplet. Okay, and these small droplet will be across. It will look like it has mixed with the whole liquid, but then eventually to regain its surface energy back, because always the the tendency of the nature is to acquire the minimum potential energy, and for that it has to have a minimum surface area. So again, this droplet, if you put for some time, this droplet will aggregate, and then finally it will become the same and the back to square one. So if you can see this and this, they are back to square one. So it is because to acquire the minimum potential energy. So this is a very interesting thing which we see in that immiscible fluid, how the behavior of it to immiscible fluid. So today we are going to discuss why I presented this particular slide. Today mostly the discussion will happen, or mainly the discussion will happen the interface between the two immiscible fluid. So and during the chemical reaction and vaporization. If you see here, the vaporization, the interface is driven by temperature gradient. Okay, that's one of the main thing. And this temperature gradient, if you see the equations which drives this temperature gradient and the interface definition at the vaporization level, is the main equation is Clausius the Clapeyron equation, which calculates both the vaporization and species mass fraction held at the interface. Species mass fraction is for any chemical process which get involved, or chemical reaction which get involved, and the interface shifts. So the same Clausius-Clapeyron equation, only there you have to take the species concentration gradient, and in vaporization we take the temperature gradient. That's how it is. So the mass transfer during both vaporization and chemical reaction generates an imbalance inside the mass conservation. This is a very important statement, because this is the statement which we are going to see in our next slide, and not next slide, I mean the coming slides, that exactly when the evaporation. So there is a two different thing between a non-evaporating interface shift and interface deformation, interface stretching, and with vaporization the interface deformation and interface stretching, they are two different. In the first case, where the interface is it is not non-evaporating case, the interface is stretching, interface is deforming, with making the conservation of the mass conservation with adhering to the mass conservation equation. So basically the continuity equation at every iterative step is getting addressed, and the continuity equation remains that the mass conservation equation remains there, and it is always adhered. But in the vaporization case, exactly, the mass conservation equation is not adhered at every iterative level, and what is happened, that creates an imbalance in the mass, and this imbalance drives the interface phenomena, which we are going to come to the coming slides. So I just wanted to put the highlight of this. Now I would like to take you to the numerical approaches which used to capture the sharp interface. So there are widespread numerical approaches have been taken from ages together. I'm not going to discuss too much of them, but the major computational expenses which already had happened in our last few decades, they are important, and I'm going to discuss mainly that. And if you see, there are three popular approaches. The one is the typical Lagrangian method, and other as the Eulerian method. Eulerian method, if you break down in a roughly, it is level set and the volume of fraction. So volume of fluid. So now this volume of fluid method is mostly adopted by all the commercial CFD tools nowadays. We'll see all these. The first one is the Lagrangian method, which we say as a boundary element method, because here what we do, the basic steps I have described, as you can see here, the grid follows the fluid. This is one important statement, very important statement. Here the grid follows the fluid. So and then few authors who have done the work, Feng and Hu, Oren and Boris. And this is a fairly complex approach, but then this approach was simplified by another author called Tryggvason, by developing the front tracking algorithm in the same, using the boundary element, finite element, one-dimensional finite element method, Lagrangian finite element method. He developed this front tracking algorithm. This front tracking algorithm really stands very powerful in addressing the interface shift, both in the non-evaporating, also in the evaporating component. Now here the one lacuna is there, since you are defining it here. It is defined like the whole interface of the let's say a droplet. It is broken in different Lagrangian element. Okay, n number of Lagrangian elements. So what we do here basically, if the because this is a Lagrangian Eulerian solver, so the basic thing will be Navier-Stokes equation will be discretized in the Eulerian cell only, but the interface and the surface tension forces will be discretized over the element on the boundary element method, and these are the one-dimensional Lagrangian element will be constructed, which will be constructing the complete interface. Always this Lagrangian element will be one-dimensional lower than the Eulerian element. If you are solving the Eulerian in the 3D, then the surface will be of 2D and the Lagrangian surface element will be of two-dimensional element. And if you are solving in 2D, let's say in this case, I have my code I have developed for 2 dimension. So here the Lagrangian element will be one-dimensional lower, that is nothing but one-dimensional Lagrangian element. Now, but here one important lacuna and the drawback is because of this the connectivity, already pre-established connectivity, this is 1, this is 2, this is 3, like that n number of Lagrangian element will constitute this, because the list you are preparing this because of the element merging you have already done in the finite element. What will happen, this Lagrangian element will never leave each other. So what will happen in case of a deformation, let's say additional deformation of the surfaces, some extra additional element will be created. But what I wanted to say, this chain will never be broken. Okay, if the interface deforms on a convex way, so there will be more number of elements will be addressed. If it squeeze, then the number of element will reduce, but it will never break. That means, I mean to say, if a droplet breaks down, so this part you will never get in this front tracking algorithm, because it will not allow you to make this breaking point, because of this the algorithm limitation, that you are not giving an allowance for this Lagrangian boundary element method to get separated, because you have defined it as an integration and the complete energy conservation happening basing on this intervention. So you cannot cut the chain. You cannot cut the chain. So the chain has to be there. More number of elements can be populated, less number of elements can be populated, but the chain has to be complete, the Lagrangian finite element chain. So that's the limitation of this. Hence, for the next level of getting a segregation of the droplet, the coalescence of the droplet, we have to shift to the Eulerian method. And Eulerian method is pretty simple, because you are capturing everything on a single grid, that is Eulerian grid, and that to fixed grid. That is one of the very important technology which have been developed. So that is the first thing on the Eulerian is level set, where a Eulerian computational technique for capturing the moving boundaries or interface you have developed. And here the main driver is the level set function, and we will see how the level set function drives the whole the level set formulation. And this level set function, the most importantly, this level set function will get distorted at every advective equation. When the advective equation will iterate, this level set function will distort, and we will regain or reinitialize this level set function back to the thing by means of a function called sign distance function. This is a very important function which we are going to discuss. In volume of fluid method, you can say it is an elder brother of this level set only. Almost same. Here the thing is that the main concept is here, every cell they are calculating the fraction of the fluid. Okay, the volume of the fluid is there, and divided by the total volume of the cell, by which you are dividing a proportion, and the interface and the normal vector, here they are tracking from this particular this volume of fluid, this fraction, that is alpha. So this is the beauty here. All the normal vector are defined basing on the distance function and the volume of fluid, that exactly how much proportionate percentage of fluid inside a particular volume. So that is almost similar. When we will explain this both the things, you can understand that there is a lot of similarity is there in these two methods. So we will come with pictorial view instead of discussing there. So if you see this, I taken it from a Google, a very beautiful picture of a droplet. And let's understand the front tracking algorithm. So here, what we define is the main Navier-Stokes equation. You have already seen this is the mainstream Navier-Stokes equation, and now the extra part is nothing but this is the surface tension part. This surface tension part, what I exactly said, this particular surface tension, you can see it's an integral over the whole length of the surface energy. So to calculate this particular surface force, and this surface force has to be just it is getting added to the main Navier-Stokes equation. Now, and this total happens now, this individual, if you see, this is happen on the Lagrangian grid, okay, and this is happen on the Eulerian grid, okay. So once the information come to the through Lagrangian grid, and once it is getting added, the total thing finally happen in the Eulerian grid. So this is a very beautiful way. You can see here. Another thing is the interface of the single droplet has been tracked by solving the Navier-Stokes. I have written here, and the main thing here is the jump discontinuity to incorporate the effect of the sudden change in the fluid properties. This is the part which we are defining the jump discontinuity by using Dirac delta function. Okay, so if it is 0, you are on the same phase. If it is 1, means the phases get changed. So, with utilizing that property, and this is a Kronecker delta function, we are making two arguments here. That one is which is at the existing phase, okay, either in the liquid or in the gas, and this x with a subscript of gamma, it represents exactly the space partial coordinate at the interface. So this part is very important here, and how we are addressing this particular change. Now, first, how the Lagrangian elements are defined over the Eulerian cells. Now, you can see at a particular part of the interface, these are the Lagrangian element as I shown. And you can easily understand this part, as we are considering I equal to 1, and this part we are considering as I equal to 0. Now, here, one most important part, first you have to understand this. Any particular droplet, it is undergoing this type of forces. This is the viscous force which is acting upward, okay. This is the force due to momentum which is coming due to gravity. Consider a droplet is falling in a natural gravitational action. Now here, how the interface being defined here, exactly this integral function, it is defining the sharp interface. Now here, this Kronecker delta function, this is we are calling the discontinuous Heaviside function. Now here, exactly to make you understand how this function works, I just made, because I honestly did not have that much time to put them through equation editor, so I put it in little hand, kindly excuse me for this. So this Dirac delta function, it exactly okay, let us consider it. Had this Dirac delta function not been there, then what would have happened exactly? Without considering the Dirac delta function, could we not have solved this previous equation, this particular equation, without considering the Dirac delta function? We could have, but the problem was, let's say without the Dirac delta function, if you solve, so your one side, this side, the interface, exactly this is the length of the interface. You can see this is the length of the interface. Okay, I have defined here, I have widened it for your visibility purpose. Now this side is one fluid, heavier, denser fluid, and this side is air, the rarer fluid. Now what happened? If you do not consider the Dirac delta function, what will happen? You will simply have to make a linear interpolation of the interface, because you don't have any other choice. Now linear algebraic interpolation will not hold correct because of the nature in which it gets the vary, and in which the interface gets its updates from all the nonlinear equations. It won't remain linear likewise. So hence we use the Dirac delta function, because this Dirac delta function, it is allowing us to develop, because you see the integral of this whole delta function, okay, over the whole region will be equal to 1. So almost you can consider it's a sort of a finally converging to a Gaussian function which have a probabilistic sort of a distribution, and you can see this probabilistic distribution I have just represented it here. Now what happened? Because you are multiplying these things over the linear interpolation of the densities, what is happening? An approximate interface is getting changed as per the iterative process adapted, because this is the change in the interface you wanted to adapt. Let's say in case of a particular iterative state, your Dirac delta function, and because of the x and x prime, I mean to say x gamma location, it got changed over the interface. So let's say the Dirac delta function distribution function will behave like this. Then obviously it will pull that time at that particular iterative state. The distribution, it will fall on something like this. It won't fall the previous line. So likewise, this Dirac delta function carries that ability to make the information getting shifted inside the interface, to make the jump from one density to other density, or one viscosity to other viscosity. So it's a property adjustment we are making by this particular function, and finally we are getting added to the interface equation. Now here already I said the interface is defined by n number of one-dimensional Lagrangian elements which are interconnected to each other, address the stretching and contraction occurring at the interface during the droplet journey. Density and viscosity will be taken as randomly, that already I have told, in the Eulerian cell, whether falling in liquid or gas medium. Upon saying this, now we have to understand the remaining part of the things we solve in typical Eulerian cell. This is, the continuity equation, as I already said. Okay, now here is the catch. Please understand. If it is a I already told it in the around 4 slides before, that for a non-evaporating interface, the continuity equation always adhered to this condition of mass conservation condition, that is, grad of u will be equal to always 0. But the moment the condition will be evaporating, okay, or any chemically reacting, this additional mass will make it, this mass imbalance will have to be addressed by this particular component, and this mass imbalance will be the main driver on the defining the further interface of the evaporation process. Okay, or even the condensation also. Now this you can do. I shown here a typical grid management. I used a staggered grid. Okay, you can see here this is the UV are getting shifted accordingly. You can do it on a collocated grid as well. There is no such hard and fast. Only thing in collocated grid, in case you occur, you come across any checkerboarding, then the solver will show some unstable behavior. But then otherwise, lot of my other codes I have developed in collocated grid with adequate safety measures, taking the added dissipation part and all. It worked well. Okay, because some complex geometry, sometimes the staggered grid, it will be challenging for you. But here, since I have developed it on a regular geometric condition on cylindrical system and rectangular system, so I consider this as a regular staggered grid approach. Now here, as I already said, that the moment the evaporation of chemical reaction is happening for the changing the interface, what will happen? The extra amount of fluid which is getting evaporated, you can see this is the fluid, this HLG, it is the latent heat of vaporization, amount of fluid evaporated. This is the gas density, and this is the density of the liquid, and again this is the interface function, the definition of the interface. And this particular thing, the overall thing, it is creating an imbalance, and this imbalance is addressed by this grad dot u. Now this, once this imbalance get addressed, this imbalance has to sit exactly this energy equation. Okay, now otherwise your energy equation used to remain up to this, but now because of this has happened, so you are in the energy component, not the exact one. What I mean to say, this the contribution, not this whole equation will sit, but the contribution, because of this imbalance occurring in the continuity equation, the similar imbalance in the energy part, the thermal energy imbalance, will be calculated on a proportionate basis, and this also has to be added in the mainstream energy equation. So these are the two important changes in the equation level we make it if we are considering the interface getting shifted because of the evaporation process or any chemical reaction process. So only chemical reaction you have to just mention it through species concentration things. Now here, if you now move to the next slide. Now here, the main thing you can see here clearly the species jump discontinuity condition. How I have mentioned the species jump discontinuity condition. So here you can see on this particular picture, I have considered a node here at this position x plus y plus, x minus y minus. Okay, now these nodes, if it is going out of the domain, because sometimes what will happen when the droplet will go towards the boundary, you may face, you are shortfalling, your boundary may come here. Okay, your boundary may come here. So at that time, on the boundary condition, this node will become then ghost node. Okay, so that also you have to take care. I have not given too much detail on this ghost node part. It is almost in the similar level you have to take care. But the main definition is you can see here, for a normal, if it is lying within very well within the boundaries, this is the main condition what we take, the mass balancing happening through this, the difference in the temperature gradient across the normal direction. That is one important thing. This direction has to be always normal to the interface. Because that will drive further interface shift at every Lagrangian element. Okay. Now here what we do, the vapor mass fraction at that interface we have to again capture by means of Clausius-Clapeyron equation, and this vapor mass fraction we have to first calculate. The vapor pressure we have to calculate, which we will calculate from this, we have the interface temperature. Okay, we already mentioned, and this is we have the fluid bulk temperature. Now the ambient temperature and the interface temperature, obviously it will constitute the temperature gradient, and basing on the temperature gradient, first you have to calculate the vapor pressure. Upon being calculated the vapor pressure, then you kindly calculate the mass fraction of this particular thing, at that particular droplet on that interface, what will be the mass fraction at that iterative step by this particular formula. So this is the equation 7. Having addressed this part, now the adapted solution process, you can please understand here the Navier-Stokes equation we don't solve on a regular simple algorithm, on a regular simplex. We don't put it like that. Here we make it as a predictor corrector type method, because there is a reason for that, because this whole solver is developed first of all on a transient step. Now what happened? The main equation is this one, the continuity equation. You can see at this n plus 1, n denotes the time. So at time step 1, time step n plus 1, we want to calculate this particular, the rho n plus 1 and u n plus 1. And this part is the continuity equation. We understand that. Now here we just break this continuity equation in two different. Finally, if you cut this portion, it is regaining back the original equation only, but then we distribute, and this advective is nothing but it is consisting of this whole advection, diffusion and gravitational and all the other surface tension term. I have dumped it everything in A superscript n. Now here and only the grad P will be here. Now what will happen upon distributing this part in this particular format? What we will obtain is, you can see here, this section, the first section, it is, I can put it as 8 superscript of n, whereas the later section I have put it as this grad P section. Okay, now this reveals an important strategy here. The important strategy is the basic thing is here. Finally, if I make another gradient operation on that particular last equation, if you see here, okay, on this u star upon, if I make another gradient function, okay, on the gradient operation on this, what it will happen here is this grad dot u star and grad dot u n plus 1. Now we know this is one part, and here it will come as grad square p. Now this forms a typical Poisson equation, and the benefit what we are getting here is, for no evaporation case, we know at the n plus 1th time step this grad dot u component will constitute 0. Okay, but for the with the non-evaporation component, then equation 3 you have to substitute. Okay, please remember. Now here what will happen is that you got, because of this grad dot you formed your velocity at the Eulerian cell as a function of pressure. Okay, you obtained from the Navier-Stokes equation, you have made it at the n+1 step. So this is one thing you have obtained from here. And basing on this pressure field obtained from the above equation, now you can see we can update the velocity at the neighboring time step. Now you can see here how we are updating the velocity here. So we are making this un+1 will be equal to u star minus this one. Obviously, it will happen like this. This is the, I have put it as 11, equation 11. Now here, one important catch is there, that these velocities you all obtained in the Eulerian system. Now you have to transfer it back to the Lagrangian itself, because finally you have defined the element of the Lagrangian element as a one-dimensional finite element, and the information on the finite element grid has to be shifted from this finite volume to finite element grid, and there are interpolation functions which are used to shift this information. So the most popular interpolation function is Peskin's interpolation function, which I have used particularly to shift from this ij to directly to the interface on the Lagrangian interface function. So this is a very much pure form strategy. Most of the authors, they adapted it, including Trygvason, also the other authors, couple of authors who followed, they all adapted these particular methodologies and this particular shifting function or the interpolation function from shifting the variable information from Eulerian cell to the Lagrangian cell. Now here I have given little detail that you can see here from Eulerian cell, you can see this interpolation function, how they are using it, where this delta sk is nothing but this is the Lagrangian element distance for one particular cell. You can kindly see this one. This particular delta sk is the length which you are measuring at a particular stretched interface at kth cell. Okay, and h is the typical grid size, depending on your, if you consider that your x and y grid having aspect ratio of 1, so h is the specific one, and if it is del x and del y are different, then in algebraic composition have to be made accordingly. So now once it is shifted to the Eulerian grid, from Eulerian grid to the Lagrangian grid, now you are at the interface, and I have just mentioned this is the Peskin's formulation. Kindly see, this is what I have used. This is the Peskin's cosine function, which is the most popularly they used, and I also use the same. Okay, in the interface to define it. Now once you got the things in the Lagrangian coordinate system, and then the Lagrangian system, the interface, exactly the x coordinate of the interface at n+1th time step, you are updating, okay, with the from the nth time step by the help of this delta t, and then the calculated the velocity which you already transformed from the Eulerian to Lagrangian by this interpolation function with the normal vector. Okay, so this is the typical, and the solution step, how the most important thing, which are the solution step we adapt for this whole process is calculating. First we are calculating this extra heat flux at the interface if it is a evaporating condition. I made the algorithm considering the evaporation is there. In case it is not there, anyway you are putting the grad dot u at n+1th step is equal to 0. So now this will be distributed onto the fixed grid using Peskin's distribution function. Then the interface advection is considered for the next time level n+1, as already shown in the by means of the predictor corrector method. And then the energy equation has to be solved to get this new temperature at this particular place for a evaporation condition. And then you can see here this is calculated at the distributed onto the fixed grid. So this is the heat, okay, amount of heat generated, it has to be distributed, and then you have to solve the Navier-Stokes equation to get this un+1. To solve this, you need the surface tension term at each frontal element to the interface location, and we know how the surface tension term has to be added to the mainstream, Navier-Stokes equation, which has to be solved on the Eulerian grid. Then updating the material properties, that is very important, because the density and the viscosity will get changed on exactly at the interface at every iterative step, and you have to address that diffused interface. And then reconstructing the Lagrangian interface grid at each time step. So obviously the Lagrangian grid has to be reconstructed based on the information so that it will get shifted at every place. Now, so this is overall, that how a typical front tracking algorithm works on a nutshell. It's a very huge part. It's not small. Actually, everything has to be. Actually, we use another inverse function, which from Lagrangian to Eulerian transformation, we make another inverse function. But it is almost similar. Hence, I have not again presented it separately, because otherwise the things will be very difficult to restrict in time, because we have to discuss a lot of things. So I have used this part, and now on the cylindrical coordinate system, kindly understand, I given a representation in my hand where I have developed from my own code. You can see here there are four basic staggering mechanism followed. One is in blue color, which is representing the pressure coordinates. Okay, the red color is the u velocity coordinate, which are the radial velocities. The v color will be the azimuthal velocities. You can see all the ij, the vij is at this e location, the pressure ij is at this central location, whereas the radial velocity location is in this particular thing, and these are the property updates. Okay, the viscosity and the density update, property update happening at this particular location. Okay, so these are the four different centers. So like this, you have to populate your grid. This is, I made it in a single color because it will be easy for you that how the grid structure you are making basically for this type of calculation, typical calculation holding on even on a spherical coordinate system. The remaining thing will remain same, only the equation you can see it will get changed to the cylindrical coordinate system. So that's the only, and you have to calculate obviously certain extra, the Reynolds stress part you have to calculate extra separate, because in cylindrical coordinate system the coordinate expansion takes little longer time. And one important thing here you have to understand very important seriously for the spherical coordinate system is, or any cylindrical coordinate is, here in the xy coordinate system, this the interface which you are defining and the Lagrangian element, the surface tension forces which you are representing in a rectangular coordinate system is much easier to represent, because on a xy coordinate system you are getting a benefit of the balancing the surface tension on a in any type, the balancing of the surface tension happening on a particular element. You can make a resolution much easily basing on the x. Okay, basing on the x and the basing on the y coordinate system, which is pretty much simple here. So this you have to take this, resolve this component over the xy, and the force balancing become very much easier here. But in the cylindrical coordinate system, it will be challenging, because you cannot take the droplet center as your main epicenter. Okay, because there will be the droplet will be inside a box or inside a pipeline. Okay, in the cylindrical system. So what will happen? The pipe center will be somewhere here, and the drop center will be here. Now what will happen is that from here, the main coordinate system will be defined from here, and I faced a lot of challenges in addressing this particular element direction, because let's say the same element here. Okay, let me change a little bit on the ink color. What will happen is, the main challenge is here to represent this particular direction, in this r and theta will be very challenging, because you have to be really careful on every delta theta addition, how this r and theta is getting changed, because in this particular every case you will have a different r. From here to here you are going to have a different r. From here to here, everywhere the respective r will get changed and its component will get changed, and the balancing of the component, you have to little struggle, but you can do it. But you have to really balance them very accurately, else your Navier-Stokes equation will be diverging, because I faced this challenge a lot of time while developing this. Hence I thought it is to be told. And for evaporation also, kindly see this particular part. You have to make this balancing, because any time the interface gets shifted in this evaporation, you have to really be careful on the gradient part while calculation of the normal vector. Every time the gradient has to be calculated accordingly, because again you are going to have the things on the r coordinate system, and in r coordinate system so in the r coordinate system, the problem is, it will happen every place if in a stretched interface and all, when you want to calculate the exact normal vector which is from this side to this side, you will have the resolution challenges will be much higher. So you have to be very careful, because the big problem is in r theta coordinate system, when you will start increasing the theta, the sine theta part, it will remain positive up to this much. Okay, and sine theta and cos theta, then it will change. The sine theta will remain positive up to this, but then the cos theta will start negative from here. So this part you have to be really careful on the domain and range expansion of the sine theta and cos theta component. This is very important, because otherwise you cannot balance your equation. Please remember, because this sine theta and cos theta you have to put everywhere, literally, to balance this surface tension component which you are going to add to your Eulerian cell. So kind for this part. So just I thought to put it to you. So this is a thing. It is I'm just the code which I have developed by myself, and the best way to exemplify is give some comparison that whether the code is running correct or not. I honestly did not get much time to put forward too many graphs and curves. I was running out of time because of the COVID situation. In office and business also had little challenges. I pardon that excuse, but I presented, however, the situation what I could able to generate. You can see here, this is the condition. I have generated one droplet of, you can see which is there at a 0.2 meter and 0.5 meter of the coordinates system. This is the center of the droplet, and if I am blowing air from this particular side on the first droplet, from this droplet. Okay, and these are the simple wall condition, the no slip condition, and this is under the action of gravity, how the droplet will perform. So this droplet is an elastic droplet, and this is a plastic droplet. You should get an understanding that how an elastic droplet and plastic droplet should behave, and whether the behavior is getting replicated over these particular things or not. So kindly see this animation if you are able to see. If you are not able to see, please let me know. My screen is running with the dynamic animation. Someone confirm me if you can able to see this animation part.
Yes, sir, it is visible.
Yeah, so kindly see, thank you very much. So see, now the left side droplet, this is because of its elastic nature, it is going to, after colliding, it is going to regain back its shape. Because of the surface tension forces will make it back to shape, but because of this plastic nature of this particular droplet, surface tension forces will not be able to make it back to the shape. And you can see it's like a sticky fluid typically. The physics also, if you see from a vertical wall under the action of gravity, how it should trickle down from the things. But whereas the left side, after completely compressed, but then it is getting back to its shape. That is most important. It is making this bouncing back action with this pinching effect. Okay. I made further some study on this pinching effect also, but then because of the lack of time, I did not present it here. And but this droplet will be regaining its shape back. But whereas this particular droplet, it is making it slide, but then it will never be able to, make its shape back. So that is what on this particular part of on the front tracking algorithm, how. But this, as I said in the beginning itself, on the front tracking algorithm, the main disadvantage is that you can't break the chain. That's it. You can't break the chain. Whatever do within this single droplet environment, you can do n number of experiments, and this is very fast also compared to Eulerian algorithm of level set and volume of fluid. This Lagrangian front tracking algorithm, transient algorithm, is much faster because the interface is defined directly by a linked list, which is defined by you. So this is one benefit of this Lagrangian Eulerian element. So I just want to put it forward for 2 minutes. I would give it to the audience back till this, because now we will be shifting to the Eulerian part. If there is any question so far on this particular front tracking algorithm of the Lagrangian element, you can ask, so that I can, then I will start the next session. Over to you, people.
Yes, participants, if you have any query, you may discuss. You may raise your hand. I think there is no query from the participant side. Yeah, Dr. Sarkar, you may continue. Yeah.
Sure. So thank you all. So now, let's get back to the okay, sorry, another the same thing. Sorry, in front tracking algorithm. Now okay, this whatever you seen, this is without evaporation process. Okay, only the interface deformation happening, but the evaporation not happening. Okay, now with the evaporation process, I captured another of my own program. So this is the literature published by Irfan and Matin. You can see here the drop is falling from here with a high temperature chamber, and the drop eventually getting evaporated and making a crescent shape at this particular location. Okay, and this the shape of the droplet is basically driven here by the two important number, that is Yotvos number and another is Morton number. These numbers which constitute the shape of the droplet, what it will undergo in case of an evaporation. These are the two non-dimensional number. And here initially the droplet temperature is at 373 degree Kelvin, and the temperature in the domain I have considered as 480 degree Kelvin, so that the evaporation should take place. Okay, now as the temperature will be more, the evaporation will be more faster, but then the numerical stability you have to be little careful, because too much faster evaporation, it may need more reduced time step. Okay, because that CFL condition also you have to say that current Frederick and Lewis, the CFL condition has to be also satisfied, because if you put a very high temperature at this particular, let's say some 1800, 1900 Kelvin, it will evaporate, but then there are high chances the solver may also diverge unless and until you reduce the time step in that particular scale to maintain the CFL condition in an optimum position. So this part you have to be sure. So kindly see this the evaporation part, how the droplet will reduce in the size as the evaporation is taking place. Okay, I could not take the contours of the evaporated component, but however you can see the main droplet is losing mass, and the interface is you can see accordingly the interface is getting addressed, and the Yotvos number and Morton number, it is properly taken care here, and you can see that you can see that the crescent shape is being taken and the droplet is squeezing in its size, and because of this particular free fall on a high temperature chamber. And as much the droplet size will be initially, let's say, as much bigger, the evaporation rate also will be that much bigger, because of the more surface area exposure, more surface area makes the exposure more. Okay, so you can see how the evaporation had taken place and the droplet size shrink. So you had seen that the front tracking algorithm, how it runs or it proves well for both non-evaporating component as well as for evaporating component. You can make it as a condensing component also, the surface condensation also, that it can be taken care all in the same algorithm. Now just excuse me, I'll take some water. Sorry, my throat got dried. Now the introduction to the level set method. Here the concept is completely on the Eulerian cell. Here you have to understand, see, let's go one by one. The level set method is an Eulerian computational technique for capturing moving boundaries. Now here the main function is the level set function. Okay, it is defined in a domain as a sine normal distance function measured from the interface. This is a very important statement. Okay, and the value of phi is less than 0 for liquid phase and greater than 0 for this gas phase. Now please understand one thing, how the definition takes place is, it is by this is a total function, is the implicit function, kindly understand. Okay, so this function is an implicit function which drives the total function, but the distance function is not. You have to get the distance function out. The distance function, let's say here it will be, that means if your coordinate system center is this, the distance function you have to calculate that how much distance the interface is from your exactly the center. So the distance function will work out like the x square plus y square minus 1. Now this is how the distance function will go as per the xy. Okay, so let me write it more accurately as d of x and y. So this is how the distance function. Now when you start plotting this at for every value, so obviously the function will be, it will be represented by concentric circles. Okay, because this is the distance function, and you see here when exactly the xy will go till the interface point where the already the radius of the droplet you have made it as 1. So obviously 1 minus 1 is 0. So what will happen? Basically the interface, exact interface, because of this distance function, will be always holding the phi value as 0. The upper section will, the phi value will be in the increasing mode, you can see here, and the interior section will be, phi value will be in the negative mode. So that is what has been said here. The phi is less than 0 for liquid phase, greater than 0 for the gas phase, and equal to 0 exactly at the interface. So this is how you are going to define, and your distance function is the regular normal function. Hence I have given the normal vector always to the interface. So this function, but please understand the difference between the implicit function, okay, and the distance function. Kindly don't get confused, because a lot of places the color function may be written as a phi. Now here what we make is the phi we are considering as the level set function. So actually the phi we consider this only. Basically this is which you are calling as distance function. Now what we do is, first this phi will be advected, okay, directly by this equation 13. That's the pattern. We directly advect this color function, okay, in the in a transient mode. So this term, alike in the Navier-Stokes equation, it just get advected. Okay. Now in the beginning you can see here it is in the beginning the normal distance function such that the phi at any grid represents the normal distance from the interface and positive and negative values surrounding it. Post advection, now the one is important thing, once the advection over, now the what will happen, the interface in after the advection will get very much in a unpatterned way, and the interface get very much diffused, and the sharpness of the interface deteriorates because of the advective nature of this particular equation. Okay, so because of this advective nature it get deteriorated. So that deterioration has to be repaired. Okay, that deterioration has to be repaired, and the repairment we are doing by means of a reinitializing the thing. Kindly remember, the reinitialization is needed at every particular step. This reinitialization function is important to get this distorted interface back to the shape. Okay, so to regain the sharpness back. So this is the main concept which drives this interface phenomena, and interface phenomena through the level set method. Now here if I tell you, kindly see this. As I said, as the interface deforms, this part always phi will be less than 0 in the inside and phi will be always greater than 0 outside, and at the interface phi will be equal to 0. First you have to capture the exact curvature, because the curvature is very essential here. Since the curvature is going to directly calculate, it will calculate the surface tension forces and the resolving the surface tension forces on the normal direction, because the surface tension forces, unless and until it get resolved in the normal direction, the further ballooning of the interface or squeezing of the interface will not happen. Hence this curvature calculation is very important, and this curvature is nothing but the grad vector. You can see this grad dot n, so there's a divergence of the normal component of the vector. Now here, kindly understand this, there is a difference, as I said in the last time also. Now here one catch is there, that how we are going to repair this interface after, because the interface is badly damaged because of this advective part. Now we need to first calibrate one, because a calibration needed at the interface, or on a method, a calibration needed so that we can gain back the same interface. Now the calibration cannot happen on the main equation, the implicit equation. So there is a very unique methodology which have been taken for this calibration. Now with an example I will start. What will happen? Consider this example of an implicit function of x square minus 1. Now see, this is the implicit function x square minus 1, but the same Okay, this sign, and you can please remember the same thing. I can represent it by this function also. Okay, if I say phi equal to mod x minus 1 and phi x equal to x square minus 1, basically these two things represent the same set of point, that is nothing but this point. You can see the mod x curve. Okay, and the phi is less than 0. That means this is the inside fluid part and this is the outside fluid part, the air part, the outside component. Now all these areas are outside and the sharp interface is this particular thing. So basically we have mapped the sharp interface by this particular modulus function, or this particular type of implicit function. There is a reason why we taken this particular as a definition of the interface modulation, or we can say we can map the interface tracking method by means of this particular function. It is because in this is a particular function where the grad phi value will be always equal to 1. Okay, because the moment you are calculating the grad phi, so any derivative against x, you are going to get 1. And because of this particular nature, for x equal to all non-zero values, you are going to get this grad phi 1. Because this grad phi 1 is the property which we need to expedite every part, okay, to redefine the interface back. Okay, that is what we are using as, and we are calling as signed distance function. This is a very important terminology they have used because of this particular characteristics of this nature of equation. That is, this grad phi will be 1 for all non x0 component, I mean x equal to non-zero component, and wherever x equal to 0 there will be a kink, and we, in numerical cases, we smear out over the kink. Okay, so our solvers smear out exactly over the interfaces back and forth, but it doesn't exactly come to the interface because of our numerical iterative values. So we don't really need to bother about the exact x equal to 0. It is indirectly defined and it will be constituted in that form. When the iterative steps will be there, it will eventually come and then redefine the interface back. So that's the concept here taken. Now you can consider here the original implicit function. If I take the implicit function which we taken here, okay, x square plus y square minus 1. In this original explicit function, x square plus y square minus 1, as I said, this is the distance function d of x. Okay, if you see x square plus y square to the power half square root minus 1, this is the distance function. But in this function, if I say the grad phi, this grad phi will not be equal to 1. This is the lacuna, that I cannot repair the interface on basing on these functions, because these functions, whether now it is circular, other time it may be something else, because as the interface will take different shape, depending on that, it may sometimes take the elliptical shape, it may sometimes take the hyperbolic shape. Depending on the situation, okay, we cannot rely on this particular function to repair the interface. Okay, because this function particularly, it doesn't always confirm these characteristics. And how this characteristic is going to help us, because this particular function, what I already told, okay, this implicit function x square minus 1 and mod, which is the same representation by mod x minus 1, this is the very much calibrated function which will exactly define the interface on a very much uniquely, that this part is the inside fluid part and this other remaining, the whole section is the outside part. A very beautiful way, the interface definition has been given, and the beauty of this is we will get always grad phi value as equal to 1. Now if we calibrate, we take the calibration point as this function. Now to any distorted interface, we can give a conditional point that the repairment should happen considering the control or the conditional statement that the grad phi of this function has to be repaired back to as near as 1. So once we will adhere this particular calibrated condition in any of the interface, so the diffused interface eventually will get straightened and will get regained back its shape, which we do by means of defining this particular function, so-called a signed distance function. And kindly see, this is very important, and this equation is called the reinitialization equation, because the reinitialization, what is being done here, please understand, the interface value, we are making a transient step here, that delta phi upon del ts. I will come to this ts later, But what is being done exactly here is basically we are forcing the phi to follow this particular nature, that grad phi has to be as near to 1. So accordingly, you have to reconstruct the phi back. This is one important point to be understand, and this is the sign function we adapted here. This epsilon is nothing but the smearing of the distance, how much you are smearing, okay, on the back and forth direction, okay, exactly on the distributed diffused interface, so to get the interface back in shape. Now you can see here the diffused interface condition, the interface was not very well prepared at this place, but the reinitialized interface, it is very well prepared. You can see here, this is the difference between the reinitialized and the diffused interface. Now here one small catch is there. Okay, you done everything, you done that, your phi will follow this particular mechanism of always it will maintain the grad phi equal to 1, near equal to 1 at to reconstruct back the interface, granted. But how you are going to sweep this epsilon, that how the solver will know that exactly I have to sweep a very small distance over the interface at every place. Okay, I don't need to go too deep, because else the things will go wrong, because the interface definition of the interface or the diffusion of the interface prevails on a very small distance. We define the distance, how we sweep over the distance is nothing but we define a virtual transient step. See, there is a difference between virtual transient step and actual. The actual transient step which you have defined, that is the total, I mean the delta t, which is taking care of the total physical time you are simulating divided by your number of grid. Okay, transient number of grid. This is the delta t, and you are making this delta t to sweep the whole the total number of all the grid to sweep over this particular time. But I am not interested to put this delta t, because if this delta t means the thing is in a particular delta t part, okay, it will because of the velocity component in this delta t, if I take this original delta t, the interface will go too much. Okay, the interface will go too much. So already we obtained what is the interface velocity, the u component we have, approximately u component we have. Now this u, if it is multiplied by delta t, the shifting will be too much, we cannot control. Hence we define a separate transient pseudo transient step, that in this particular pseudo transient step is nothing but it is our control. We are just saying 10 step, depending on your pseudo transient step, how much you have considered. Okay, this 10 step will be exactly taking the value of the 10 small transient step of your choice, delta t, which exactly the u, the velocity of this exactly delta t time should not exceed this small value of epsilon. So that means this transient time step is very well defined within 5 to 10 number of iteration, inner iteration only, which will allow the main solver to navigate a very small distance over this interface. Hence, we are defining this pseudo time step. Okay, so the main time step is going on the main loop. The main time step is going on in the main loop, and this is the main loop where the main time step going on, and this is a small loop, a pseudo time step is going on. This basing on this pseudo time step, this is going to navigate over the small thickness. So that is what is the beauty of this pseudo time step, and this is the the sign distance function, how this is working. Now the most important part, you kindly see this one, the main, as I said, the Lagrangian front tracking algorithm is typically lagging the segregation and the coalescence part of the droplet, because of the linked list nature of the defined Lagrangian finite element chain, whereas this particular method can do the neck formation region, it can do the segregation and coalescence because of its, it is completely defined on the Eulerian property. First, let us understand how a neck formation zone will happen on the segregation and coalescence of droplet will happen. So basically there are two different energy which balances this drop. Okay, now what are the two different energies? Potential energy and surface energy. Surface energy is developed by the surface tension. Potential energy is by its own weight. Now if I see, I made this is not a very scaled graph, an approximate understanding. when the droplet size is very small. Okay, consider a droplet size is very small. Now in this condition, what generally happens is always you find its potential, its surface energy. Okay, the surface energy will be always greater than the potential energy. Okay, because of its less mass. The potential energy is a function of mass, and you can see here the potential energy is a function of mass. That's why I have made it mass is nothing but it's a density into volume, and it is proportional to this r cube. Whereas the surface energy, it depends on the surface tension and the area of the surface of a sphere. So I made it as a 4 pi r square. Okay, because it depends on the r square. Now what will happen? Initially, you can see, the potential energy was less and the surface energy was more when the droplet was small, because surface energy is more here, you can see, and potential energy is less. But as the droplet grows in size, so obviously the growth of the r cube will be more compared to the growth of the r square, and that's what is happening here. As the droplet grows in size, this potential energy grows significantly higher, and eventually, one point will come where it will exceed the surface energy, and exactly the breakup happens here. Before breakup, what are the stages? From the beginning, when the droplet size is very small and when the surface energy is much higher than the potential energy, this is a very stable phase. We say it as very stable phase. Okay, then as the size starts growing and the surface energy, the increment of the and the gap between the surface energy and potential energy start reducing, this particular part, the neck formation starts. You can see here the neck formation zone, it begins, the neck formation zone. Further, it is as it grows, the this particular gap between surface and potential energy is almost negligible, almost very narrow, and this becomes very unstable zone, and the oscillatory behavior and the oscillatory regimes are found. Though I did not make the study for the oscillatory regime, just informing you, this oscillatory regime will found, and the moment this will happen, the surface energy is going, potential energy is going to exceed the surface energy or equal. Exactly, the breakup will happen. It will tear from the original droplet. Okay, so that is how the things will be in this particular condition. Now I will just make you, in my own code, this is a 128 GB RAM in a 32 core processor, with a grid point of almost around 150 by 150 grid points. I have captured these two. So the left side you can see here is the, let me run the animation, and I hope you can able to, Dr. Rath, if you can confirm, if you can see the animation. You can see the left side.
Yes, we can able to see the animation.
Yeah, in the left side, one droplet is falling over another droplet, and you see the merging happened between two droplet exactly. And here also two bigger droplet, it fall on a swimming pool, and you can see how the neck formation regions are addressed. Okay, and these neck formation regions, eventually it creates, you can see secondary and tertiary droplet. Now here there are some corrections to be made, which I did not get time to make. Actually, I solved this is in upwind method, but the problem is the upwind method. You can see the droplets are getting diffused, and they are eaten up by themselves. Now this can be, these droplets, the smaller droplets which are eaten up by the solver, you can recapture them back. Okay, I'll just show it once more so that you can see. So these smaller droplets, you can recapture them back. You have to use a fifth order Venno scheme. That is a very good scheme, which I started developing, but then I stopped in between. I did not get time. But in the Venno scheme, lot of published literature, they reported these smaller droplets which are getting, diffused by, it is eaten up by the solver. It won't. Okay, it will come back to the main, and the mass conservation will, help very much strongly. So because of the diffusive nature of this upwind scheme, we are getting this little bit, the smaller droplets are unable to return back to the main mass. So this is only one problem, but here you can see the, the coalescence and the segregation of the droplet happens through the level set method. So now, as I said, it's the elder brother is nothing but the volume of fluid method. And in volume of fluid method, it is, I would say, it is pretty much simple. Okay, the thing what they made is that, you know, a function f they defined, and this f function, it is 0 if the cell occupied by fluid 1, if it is 1 if cell occupied by fluid 2, and it is between 0 to 1 if the cell occupied is partially filled. Obviously, you know, if it is half filled, it will be 0.5, it will point, it's like a decimal varying from 0 to 1. It's very easy to understand, and the properties will be varied over this. Okay, and this Fij parameter, this will govern the main property. Excuse me, just I'll take some water. Now so this is now the same way, this Fij, and in the mu also, this Fij parameter, you know, it you can see the property varies with these Fij parameters. Now here the main catch is the continuum of the surface to CSF model. Okay, what is this CSF model? This surface tension they assume as constant. Okay, so what is happening is this, basically they are taking the surface tension is nothing but they capturing from the curvature. Okay, the dividing the curvature by the surface pressure. Okay, so basically the surface tension, they sorry, I meant to say they are capturing the curvature from this surface tension. You can see here the surface tension is defined, and from the pressure gradient and the surface tension, they are capturing this curvature. And from this curvature, so once the curvature is captured, now from this curvature they captured the normal vector component. This is very important. So because the curvature once is known at every integral point, they capture through this formulation the normal vector component. The normal vectors you represent it by this, you know, del f upon del x and this, and that, you know, this del f upon del x and del f upon del y, once that part is known, from this normal vector the curvature is already known from this surface tension vector, and you know, you are capturing the normal vectors, n vectors, because you know this f assumption is already with you. This Fij parameters is calculated from a guess value. Okay, so basically you are updating your normal vectors, and they see here they have constituted a Poisson's equation against this part. And what they are making here is at a particular constructed interface, okay, where they have lot of assumption, northeast assumption, southwest assumption, northwest assumption, a lot of assumptions are there. Basically the distance d they are calculating from this nx and ny component, okay, at the coordinate system of space coordinate, when the interception is here x and this interception of this a is y. Okay, so like this they are making this interface exactly addressed, because they could able to know the n values, the normal vector values. The normal vector values are being calculated, and on an iterative basis from these normal vector values, the f values are again iteratively updated. Now there are, in lot of places there are different algorithms adopted. Let's say in one cell you get a the curvature of the volume of fluid method given an interface of this, and another near neighboring cell given an interface method of this. So they made a middle point, you know, midpoint section. In the midpoint linear approximation, they merged these two things, and both will be going through this midpoint like this, correct. And later they developed some more you know, improved methodologies with nonlinear interpolation, piecewise interpolation. And I have not personally done much research on this volume of fluid, honestly. I just know it upfront, you know, because I have a very good fair idea about the level set method. But this one, you can see, you know, with a more grid and more improved methodologies, you are basically tracking the interfaces very accurately as on when you are improving the grid quality. So that is, and higher order polynomial approximations are considered for improved matching of the interfaces across adjacent cells. This is what is being done in this, basically in the Navier-Stokes. Now all this whole thing, now I will expose you to my SolidWorks flow simulation solver, which completely follows this volume of fluid method, and you can see this complete sloshing effect, how it is considered in this volume of fluid method. And you can see the chambers which are getting filled from a particular, you know, tank to a different tank, and how beautifully the sloshing effect is being taken in our solver. So this is, I'm talking of the SolidWorks flow simulation software, and in this particular solver it is very well capable of taking this free surface flow which is addressed by this volume of fluid method. And we have really a very powerful solver, VOF solver, and which can address lot of problem on a realistic situation in pumps, in valves, in the cavitation part, and a lot of other parts. This free surface has a very strong influence in the CFD fraternity. Now you can see that the tank drainage using free surface flow. Now there is a difference in the tank drainage in using free surface and tank drain, making the tank drainage using theoretical calculation. In the theoretical calculation, you can be using maximum the Pascal's and the Bernoulli's equation, and the Bernoulli's equation will give you just the gradient based evacuation, but it will never give you the what is the imbalance is created in the surface because of sudden in the meniscus level will get down suddenly if you make the tap, this particular tap open. That cannot be addressed. This meniscus and the changes in the flow, it cannot be addressed by means of a Bernoulli's equation, where you need a full level of Navier-Stokes equation with a free surface phenomena to be captured to exactly understand the time of evacuation or time of drainage to be addressed in this particular any chamber you are making the draining system. So here I have considered a typical problem where you can see a tank with a level of 3 meter, and the maximum water level before is, you can see here almost it is full 2995 millimeter, and the orifice have been kept 745 millimeter to the center line. The inner dia is this much and the outer dia is this much. And with this, we have calculated within the SolidWorks flow simulation solver how much time it should take and how much realistic it will look like. Kindly see this, we got a drain time of approximately 47.5 seconds, and you can see with a flow rate of 17,676 liter per minute. And this is the Bernoulli's calculation. Bernoulli's calculation says this, and this is the CFD calculation in our solver, and we got a difference of this much difference, and it's not a small. It's a pretty much a big difference. 296 liters of difference you are getting. So, and you can see here the drain time, we are getting a difference of 2.11%, and outlet flow, you're getting a 1.68%. And if you see here how the draining happens with the free surface, kindly see the address of the surface, how the free surface is important in exactly addressing, and the graph is exactly adhering to this particular constituted curve. So that is what we have shown here in the SolidWorks flow simulation. The another important feature in SolidWorks flow simulation is the Lagrangian approach of the post processor inside SolidWorks flow simulation. So in our SolidWorks flow simulation, we have a one-way coupling method. Okay, so once the post processor solves the core Navier-Stokes equation with all the free surface dynamics, so this one-way coupling method, we just consider this equation, and this equation being numerically integrated to get all the particle values, okay, on the solver. So this is how the things are updated. It is one way. So only the fluid to particle interactions are taken care, but the back particle to fluid interactions are not taken care here. So but most of our problems are getting addressed in this one-way coupling very beautifully and very promisingly, I would say. And the same thing on the temperature side, on the thermal energy equation, you can see this is also numerically integrated to see that exactly the particle temperatures are calculated once the post processor runs. We just numerically integrate this particular equation so that the particle temperatures will be calculated as on when the fluid distribution happens. So here you can see this is a sort of a cone, this is oil catch can. So here it is there are a lot of particles are entering, and here there is a oil, and then as it will make the rotation, okay, centrifugal action, the particle will get segregated by its centrifugal action, and the oil will basically filter out and it will get drained on this particular lower object, the lower tank. So I'll just make a brief case study of the sewage water treatment plant. That is the most important nowadays study is being made, and the government of India is giving a lot of focus on this sewage treatment plant and their implementation in the apartments, in the commercial blocks, because to save our live water bodies from being polluted because most of the cities are now charged with this particular, the government are charged with this allegation that they are allowing the private contractors, and a lot of private contractors are not adhering to the government norms, and they just like that, they release the raw sewage outlet to the live water bodies, which is very dangerous, and our future generation will suffer for that. And this is the right time when we should cater our research on something to this segment, which will give some value in terms of humanity, or protecting the humanity in future. So the contribution of the solid works flow simulation in addressing this STP. So first let us understand how the STP works basically. So the STP process, the sewage treatment process, works in the aeration. The main concept is here lying in the aeration tank. Actually, first the raw water being collected, and once the raw water being collected, in the raw water there are a huge concentration of methane and carbon monoxide are there, which is very much injurious to the water as well as our health. Now what in this aeration tank happens is that in the aeration tank they make the oxygenation, so they add the oxygen and they make the oxygen rich inside the aeration, and the moment upon you put the oxygen, this CH4 reacts with oxygen and it forms CO2 gas is taken off, and also H2O is being formed, and like that, this oxygen helps in the proper oxygenation, and also this poisonous smoke will come, poisonous gases will get turned to the normal gaseous mode. And then there is a classified settler, and in this settler they take the little purified form of this water, and then different by, they take the sludge to the different level and making bacterial treatment for the sludge. In that segment we don't cater. Our main concept to work in this aeration tank, because we closely work in Bangalore, lot of companies, because in Bangalore it's the major companies of STP you will find in Bangalore and Pune. So big STP companies like Ecotech, like Green Waterhouse, there are so many, STP companies, I forgot the names, and big STP companies are there. So our main focus being a CFD, this aeration, because why the main thing is not, our focus is just because the fluid dynamics is there, our focus is there. It's not like that. The challenge is there in the aeration tank, because all the STP manufacturers, they are facing a challenge, is most of the STP manufacturers are not very well equipped with this CFD methodology. And what is the main problem? So in STP, there are basically two different type of STP which are mostly popular in the middle scale segment. Okay, that is EAS segment. EAS, this particular term is this is the most popular segment. This is named as extended aeration activated sludge. Now this extended aeration activated sludge is one method, and another similar method is there, MBBR. Please remember this MBBR. These are the mostly popular methodologies followed in Bangalore and Pune across all mid-size, big-size apartments, because the other method are very much expensive. In US and all, they follow some other methodologies, but then they're pretty expensive. But this works out to be very good and potential for Indian, and the maintenance cost is very low. So this MBBR stands for moving bed biofilm reactor. Now in these two technology, the main challenge these people are facing is the oxygenation does not happen uniformly, because what these people do, these people just put a mixer, and in that mixer, a mixer blade in the huge chamber, and in the huge chamber a simple mixer blade, if they put, they don't even know that whether the oxygen they are pouring in, the oxygen in such a huge chamber with this existing flow rate, how far proportionately or uniformly or homogeneously this oxygen get mixed to this this activated chambers. Without the knowledge, they take out the water for the further treatment. Without the oxygen being mixed properly, they take out the water, and the water stinks with odor and it looks brownish, and it is actually not advised to leave to the live water bodies in this form also, because the water has not been oxygenated proper, and the major challenges is at this particular. Apart from this, also some small challenges are there, because in the STP system the chambers with wastewater contains lot of immiscible small particles as dust, sand grains and mud particles. Okay, and these sand grains and mud particles, they cause erosion in the pump, because the pump are continuously moving, so many mud particles and all they are pumping out, and the pumps and the other hydraulic equipment, whatever they have, valves and other things, they all will get eroded over time because of this mud particle. So at least we can have an assumption that how much amount of erosion can happen. So our Lagrangian particle tracking solver, okay, it can really simulate well that how much amount of erosion can happen in terms of millimeter per year basis. Okay, if this particular sand grains of this particular micron size are being mixed with this particular flow condition. So that's the one of the benefit in our solver, solid flow simulation solver we have, and we have used it extensively in our STP segment. And kindly see here, this is a tank. Let's say you have constituted a very big tank and you have only one mixer. This is an example case. This is because as per the agreement we have some end user agreement. We cannot break that protocol. We cannot show anyone's model here. Hence, we have to. I just made a example model to showcase in front of you what is the exact challenge so that you can understand. So here what is happening is that they have a mixer. Somehow they have put with the curly blades and some blade arrangement, and they are putting the oxygen bubbles inlet just to make the oxygen to be get mixed. And this chamber is full of water. Okay. Now this chamber is full of water, and this is an atmospheric condition. This is to some other gases and all, CO2 and all. After being framed from the methane, the CO2 and all will come out from this chamber. Something in that way. Now they don't know whether these curly blades are enough to generate the particular amount of mixing dynamics inside the water particle, so that the oxygen will be really mixed properly across the chamber. Here, compared to the chamber, I have considered the mixer is pretty big, but they are taking sometimes the chamber will be very big, but the mixer probably, first of all, the mixing location of the mixer somewhere put here. Okay, sometimes the mixer will be put some other end. So there's no, and even if it will be, the mixer will be put at a center, this only one small mixer is not sufficient to uniformly mix the whole sewage water, because it depends sometimes. You may be thinking that what is the problem? We are mixing, we are stirring the sugar inside the tea and it get mixed with a simple action. But here it is not, because depends on the apartment. Let's say some 500 flats are there in an apartment on a particular summer vacation. Okay, the sewage load will be less in terms of gallons per minute, if you see, or in terms of liters per minute. The sewage load will be pretty less. But in the school running season and in after July and this peak season, the loads will be different. So what will happen is that as the load will get changed, and then from morning, let's say from morning time wise also it varies, because we have some observations and literature studied in that field. We've seen those literatures. In the morning 6 o'clock to 9 o'clock, the load of the sewage load will be very heavy. Okay, and that time the input and the output of this particular conditioned water, okay, treated water, has to be same to maintain the uniform content of water inside the chamber. To make that, if in a high loading condition, your mixer should support that homogenization of oxygen. In a low loading condition, maybe your mixer is well capable of making the homogenized mixture. But then when the load will be double and tripled during the morning hours, is your mixer doing the same job efficiently? That's a big question. Because if it is not, then our lake bodies and all, where you are finally disposing the polluted or treated water, it is not treated, it is yet to be treated, and some measuring part has to be there. So what we have done, we just considered a flow rate of the oxygen like this and the diameter with this tank of this. So we made our case study and we shown and we proved. Initially we had to struggle a lot with this because people are not ready to understand, but then eventually they respected the methodology and they understood that yes, if in our solver the way we mixation happens, and how they understand that a whirlpool, a vortex is being created at this place, and completely the mixation is not happening at this particular region because the low pressure is being constituted here because of this mixture geometry and the container geometry. Now that means, see here, almost 40% of the region of this particular, you can see here, if you take an image, this particular region blue color, if you shade it, it constitutes 40% of the the container of the chamber is not being properly mixed. Okay, because of this particular low pressure region, it is not mixing properly and the oxygenation is not happening correctly. Okay, so these are the things which you can do by means of using our solid ox flow simulation. Has very robust modeling method in any number of tank and any type of model. It can generate very easily because of its very powerful 3-dimension modeling solver. So here what we did is we simulated the transient mixing process by means of Lagrangian bubble flow solver, which is a part of the Lagrangian particle solver, and we seen that how the homogeneity get established across the tank and how much time it will take for your geometry of the impellers or your geometry of the tank and your construction of the tank and which section of the tank this impeller are mounted. So kindly see, and I hope Dr. Rath, last time you kindly confirm me if the things are visible, because the
Yes,
oxygenation
yes,
is,
it is visible.
yeah. Now you see the oxygenation is happening from this particular part. It is getting poured in and inside water is there, and please see very carefully that how the mixation happen, how much time, whether the oxygen bubbles are capable enough to being transported each and every corner of the container in a equal concentration manner. Okay, because this oxygenation is a very important step in sewage treatment plant, and if this oxygenation is not done correctly, you cannot remove the methane, you cannot remove the carbon monoxide, which will pollute the environment as well as it will pollute the live water lake body. So this is a very important. So now basing on this solver, you can able to really see how much the oxygen concentration is happening uniformly on this particular tank, and basing on that you can take a decision whether one impeller, let's say you have a restriction of the impeller size, your manufacturers doesn't supply more than this size, then kindly install 2 impeller, or you can make it smaller impeller in mounted in 2 different corner of the the tank, or 2 different elevation of the tank also sometimes, because if it is a very big tank with a very high level of elevation, sometimes putting the impeller only at the bottom may not help you. You may need to make the impeller in a hanging position, so that the mixer impeller should be somewhere in the middle of the elevation, complete elevation of the water. So it depends, because unless and until you have a complete 3-dimensional solution process, you really cannot optimize this process. Hence, our solver, solid ox flow simulation solver, has really been instrumental in this particular aspect in the sewage treatment plant address, and the number of impeller you need to mount at which location, at which elevation of your big container, at which locations at different places, what should be the geometry of the impeller to make the mixing process more healthy, more homogeneously, so that the methane and the carbon monoxide can be completely taken away from the raw water. So this is what our solid ox solver. And the part which I already told, because of the muddy particles, okay, you can see our solver can take the exactly how the particle will continuously bombard against the walls of different, because this mud particle will bombard at different section of different hydraulic assemblies, and you can see the display, they will display the result in terms of millimeter per year. The erosion rate has been given. The font is very small, hence I have written here clearly the erosion rate happening at which corner and which are the places you can expect a maximum erosion because of your flow dynamics inside your given geometry. So basing on this particular thing, you can really calculate well whether, see, we can't stop the erosion, but then we can minimize the erosion by using computational fluid dynamics, and especially our solid ox flow simulation solver, the Lagrangian particle solver, can really address it well, because it can tell you exactly the which portion of your given geometry under existing flow condition will undergo maximum corrosion or will prone to undergo maximum corrosion. By changing a little bit on the design, you may reduce that particular erosion concentration on a particular pocket, and you can distribute it well, so that overall erosion you can reduce on a particular segment, so that your component damage can be stopped and prevented. So that is what the solid ox flow simulation solver is made for. And with this, I would like to conclude my presentation on this whole thing. I thought a lot of things could have been presented more, I agree, but always there is a next time. And because of all this time constraint of because of this COVID, because of all this other business related issues, I could not really make it very extensively bigger, but still I tried my best to present you forward, like, whatever best possible my understanding and my application of the software on this particular tool, to the best possible way. So thank you for all your attention. Thank you, Dr. Rath and Dr. Mohabbat, for
Yeah.
your invitation to this particular. I felt very happy in presenting here. And excuse me for certain handwritten notes what I made to make you understand the interface part, because I did not get even the equation editor. So thank you
No,
anyway.
it's fine. It's really a wonderful lecture session where you have very nicely explained actually the droplet dynamics and such a complex transport process. You have explained in such a lucid manner. Any layman can understand. I hope our participants might have enjoyed a lot. So I'd like to request our participant, if you want to have a small interaction, Dr. Anjan Sarkar will be glad to answer your queries. Please.
Dr. Anjan, I have joined. Good morning.
Good morning, sir. How
Swarup
are you?
Mahapat, everything fine. I just heard your lecture. It is really nice. Of course, I couldn't attend full lecture, but the complex phenomena you have addressed in a so simplistic way, and the handwritten part is so good. Means how you are involved in your presentation. That is a reflection of that. So I think participants must have enjoyed your presentation, and really I remembered. I mean, 15 years back, this interface phenomena to track the thing. It was so tough, and I, though validated, but it was denied by the reviewer that no, this paper you have referring, that is also not correct. So that is such such a
Oh, I
tough
see.
thing. I mean, that interface tracking, and you have really in a very elucidated manner presented. So thanks, Anjan, accepting our invitation, and thanks, Prasanjit, to have you to in this particular platform. A fantastic
Thanks so
presentation.
much.
Thank you, Anjan. Thank you.
Thank
Now,
you, sir.
participants, please
Uh,
have your queries, and this is a right opportunity for all of you to
yes.
come across Dr. Anjan Sarkar, who is very normally volunteers to present, I mean, clarify all your doubts, and also ready for futuristic collaborations and like that. So please come forward to have your queries. Please.
Yes. Participants, any query you can discuss. Yes, Professor Lakveer. Yeah,
Yeah.
please.
Okay.
Yes.
Yes, sir. Thanks a lot for sharing such a good presentation. We really enjoyed it. Okay. In the last part of the slides, as you have shown the bubbles, bubble dynamics we have discussed. Was that based on one-way coupling or two-way coupling?
It is, sir, one-way coupling, because the droplet, I mean the bubble dynamics in the Lagrangian solver which we solved, it is a
Okay.
SolidWorks flow simulation we have used, and that is a one-way coupling, which
Okay.
I
So
mentioned it.
okay. So
Just
is there any possibility of two-way coupling, or
in future version you may expect, but honestly, our all users who are using it, they are happy with one way, because see, when we are taking the particles in a very much on the micron level, it really doesn't matter the second way coupling, unless and until your particle size becomes significantly bigger and more than, let's say, somewhere 100 microns plus, or 500 microns, 200 microns plus, it uh, so unless and until it becomes 200 microns or 100 microns plus, the other coupling, the particle to fluid coupling is, I mean, we did not feel it in any of our users who are using these things. They are happy with this one-way coupling, because this one-way is important even for a 5 micron, 10 microns particles. It is very important, because you see our Kent purifier, which we are using in our home, is the most popular purifier. If you see, we talk to the Kent purifier also. We are closely working in a research project, which I cannot reveal at this moment. But you have seen, if you see on the maintenance time of the Kent purifier, after the complete purification process also, you open the tank, which is the 8-liter tank fitted in, and you will see micron level particle settlement are still there on the beneath. Okay, if you open it after 1 year and 2 years, so this micron level particle, it get even slipped over the solid filter membranes. All porous membrane it exceeds, and it can break all the impedances offered by the porous membrane, and it can come. So because of the flow dynamics and this, how these micron level particles are really getting settled all over the gadgets of whatever you are using, whether you are using Kent, or you are using a sewage treatment plant, or you are using a pump which is taking mud particles. So I mean, the one-way coupling so far given us very good customers, I would say directly, because we are making business out of that. Two-way coupling, maybe it's an additional hand for researcher, but I cannot say immediately how far the corporate bodies will get benefited of the two-way coupling, unless and until some potential application will be really there to use the second coupling method.
Okay. Thanks very much, sir.
Hello, Dr. Sarkar. It was a nice presentation. I have one query related because I am working on solar thermal applications. In solar thermal applications, mostly forced convection boiling is mostly predominant in the absorber or the receiver tubes, and it's a very complicated thing because the feed flux along the length of the pipe is not constant, and the pressure drop will be there also along the length of the pipe. So there is continuous change of phase as well as change of pressure. So how to deal with these type of problems regarding this forced convection boiling in absorber tubes with net heat flux? It's not, the heat flux is not constant all over the length of the pipe.
No, I feel you can, sir. I feel so far I have, because this particular phenomena, especially this level set method, I have used it for you can see already. You've seen for evaporation, I have used it already. And I have not used it for a complete length of pipe, but then on a length of wall, I have used it. And yes, the heat transfer and the accumulation of the droplet, it is with a changing heat transfer coefficient. I addressed it for a very smaller length, I would say, may not be for a very big length, because I initially in the beginning of my lecture, if you were there, I did complete this development for sake of addressing the droplet behavior and the heat transfer dynamics happening on a plasma tube, which is a quartz tube, and the tube used to get cracked in our spectrometers because of this droplet accumulation. Suddenly the heat transfer characteristics get changed, and because of a sudden high heating temperature, 9,000 to 11,000 Kelvin, if this droplet will get accumulate on the and small droplet will make finally bigger island. Okay, that is another part we have to address, and this bigger island, two-way it is detrimental, is that bigger island, because of its sudden jump in the temperature at the glass surface, it used to crack the glass, quartz glass of the plasma torch, and this bigger island used to fall on the exact plasma where the flame is there on the flame, and it used to extinguish the flame. That is another danger part. So two-way it was detrimental for us. So I measured it for few millimeters, I mean around 10 to 20 millimeters, and I got a variation in the heat flux characteristics. Well, but on a few meters, it may need I feel it's a scale up of the computation ability, but the mechanism should be same only. Because here the complete evaporation have been modeled, and the adhesion, and you've seen in the adherence, the plastic fluid part which I explained, how the droplet is sticking to the wall, and the adherence of the plant, and the time with which it trickles down finally. So this complete heat transfer you can address on the wall to fluid part. I believe just you have to extend it to the computational ability part, since this phase change solver consumes a lot of computational effort, because I solved all this problem in 128. I mean, especially these Eulerian cells. I'm talking of mainly level set method. I solved it in 128 GB RAM with a 32-bit processor. And it taken 56 hours of time to simulate those things what you have seen. So you have to scale up the processing ability, and then you can able to solve with this model.
Yes, thank you very much. But how to deal with this net? I mean, different heat flux, various heat flux in the length of the pipe. So I told you the heat flux is not constant all over the length of the pipe. It varies
See,
from inlet to outlet.
absolutely. And you had seen, can you see my screen? If I go back here, exactly the thing which I defined here. If you see this particular slide, sorry. See, the heat flux, automatically you will get it different, because kindly see this, because the temp. So here, the moment it will be near boundary, this node will act like a ghost node. Okay, and what will happen on the wall? If a wall will be there on this particular location, and your droplet will get stick over this impinge. Let's say it got impinged over this part, right? So here you have the property of the droplet and the property of the wall you have already mentioned. Okay, so what will happen? The complete temperature, the temperature gradient what you are calculating from here, which is constituting this heat, right? This is coming from the droplet evaporation, and from this constituting this heat eventually you have to make another equation of the heat getting transferred, finally conducted back to the wall. So that equation you have to just supply there, so that the energy balance at the boundary will obtain. So this Q will be equal to, you have to write one another line is about that, K into the thermal conductivity of the wall and into the temperature gradient it will constitute on the wall side. And then this balancing you have to establish, because I did the same thing, and on the plasma tube I got a variable heat flux only over the 10 or 20 millimeter length, because I will just exactly tell you how the plasma torch was. It was just like, see, this particular portion, the coil was there, only 2-3 turns. Okay, so the flame used to happen here. Okay, but the nebulizer, all the atomized small droplets used to get enter from here. Okay, now what will happen? This droplet will get stick over here, here, and also here. So like this, over a span, this droplet used to get stick. And here the droplet will be highly evaporative, because of it is coming under the flame range. Okay, and here the droplet will be less evaporative. So always when I used to take the accumulation and the heat transfer coefficient, always this heat transfer coefficient will be varying, from higher to lower only, with this few millimeter length. I hope I could able to clear, I mean, that point. What do you ask?
Okay, sir. Okay, thank you.
Thank you.
Anybody is having any other query? Yeah, I think there is no further query. So I'd like to thank Dr. Anjan for sparing his out of his busy schedule, sparing some time with us and giving this lecture on such a complex process of phase change involving droplet dynamics. So hope to have a strong collaboration with his company in our near future. And I'd like to request our participants also, please be in touch with him for any future collaborative work or any help if you need in future.